Hello, everybody. Welcome to my student talk. My name is Helmut Hörner. I'm a student of this very university at the Institute of Theoretical Physics, group of Stefan Rotter. And I mean, it's a tremendous pleasure for me to be here, and would like to thank the organizers for making all this possible and for so very kindly inviting me to give this presentation, which will be about a special type of coherent perfect absorber, or CPA for short. So a coherent perfect absorber, CPA, for arbitrary wavefronts. So in the next 15 minutes I will give you a brief introduction into CPAs in general, and then I will talk about what makes our CPA so special, and this is something that we have developed together with the Hebrew University of Jerusalem at the group of Ori Katz, who did a tremendous job in the experimental implementation. Well, let me start my presentation with a maybe quite obvious statement. Absorption of electromagnetic waves is essential in many applications. I mean, obviously, if you think about it, you have mobile phones or solar cells or imaging devices. It's always that you want to get as much of the energy of the electromagnetic wave absorbed in the device as possible. The trouble is, quite often the device that should absorb the energy is an inherently weak absorber. So and often quite thin also. So somehow we have to solve the problem: how can we possibly get all the incident wave energy, or as much as possible of the incident wave energy, absorbed in this weak absorber? And it turns out that seemingly physics already has an answer for that. But there's a catch, as you will see. And the answer is we have to use a so-called coherent perfect absorber, which will do the trick. And this is something that's around for a while now, and it's a well-known concept in non-Hermitian photonics. And this is a concept of a very simple implementation of a coherent perfect absorber. So the trick is we put the weak absorber into an optical cavity, which in our case consists of a partially reflective mirror on one side and a totally reflective mirror on the other side. And then it turns out there is a critical coupling condition. In this configuration, it's like that the one-way transmittivity of the weak absorber should be the square root of the reflectivity of the input coupling mirror. But anyway, there is this critical coupling condition, and when we meet this condition, then the input coupling exactly balances out with the dissipation in the weak absorber, and then suddenly all the incident light gets trapped in the cavity and no light escapes anymore. And I mean, I still find this astonishing. Imagine if the left mirror has the reflectivity of, say, 0.99, then it usually reflects almost all the light. And then you put in a really weak absorber with a transmittivity of square root of 0.99, which is almost 1. And then suddenly all the light gets trapped in the cavity and gets deposited in the weak absorber. There's a way to understand this as an interferometric effect. So if you do the math and calculate the light field in the cavity in the steady state, then you see if the parameters are just right, then the outgoing wave has just the right amplitude and the right phase to perfectly cancel out the ingoing wave. So that's good, right? I mean, that's exactly what we wanted. Problem solved, no more research required. Well, not quite. As you might guess, of course, this only works if the incident light field is very special. In this case, it means like the incident light field should have a propagation exactly orthogonal to the input coupling mirror. Otherwise, you wouldn't have this interferometric effect. For any other light fields, like if you have tilted beams here, or could be plane waves also, of course, the interferometric effect breaks down and we don't have a coherent perfect absorber anymore. And this prevents possible use cases for CPAs, or has been preventing possible use cases for CPAs so far, because the traditional CPA only works with really specially engineered incident light fields. So if only we could somehow build a cavity where any ray gets somehow imaged into itself after each round trip, then we could have this interferometric effect for any spatial mode. And if we can have it for any spatial mode, then this means we can have it for any whatever complex input light field, because it's a superposition of all these modes then. And it turns out we can do it. And that's the solution we came up with. It's rather actually a quite simple concept. Again, we have the cavity and we put the weak absorber into this cavity, but this time it's a degenerate cavity. Well, what does it mean, degenerate cavity? It means that any input light field, like this beam here, is imaged into itself after each round trip, and therefore we again now have the possibility to create this interferometric effect so that the light beam cancels it out. But it's not only this light beam, of course, it's then any light beam that enters the cavity. So that's it's easier to visualize it with light beams. Of course, it's also true with plane waves. So in our case, we realized this degeneracy with these two lenses in a telescopic arrangement, as shown here. And the total length of the cavity then is 4 times the focal length of the lens, and hence it's also called a 4F cavity. So that's the trick. You might think, wait a moment, something is wrong here. I mean, okay, each ray gets reflected into itself, but obviously they have different lengths, right? If the ray comes in horizontally, then the path length is different from a ray that comes in at an angle, then it has a longer trajectory inside the cavity. And that's right, actually the physical trajectory is different. But if you do the math, then you find out that the optical path length is really almost the same for all the rays, and therefore it really works. And we did extended numerical simulation to show how well it would work, and then our collaborators in Israel did a tremendous job in doing an experimental implementation. So this is a sketch of how the experimental implementation looked like. You have the degenerate cavity here on the right side. On the left side, there is a frequency stabilized laser with 633 nanometers, and then SLM, a spatial light modulator, where you can control with a computer then the amplitude and the phase of every pixel, and therefore you can create any whatever complex light field you want to create. And then they coupled in this light fields they created, and then coupled out the reflection into a camera to find out what the effect is. Yeah, and I should mention, instead of tuning the laser wavelength, the experimenters moved the rear mirror on a piezo stage, so slightly changing the length of the cavity, because it was easier to do that experimentally. And this is the result of these experiments. On the left side, you see one of the used complex light fields. It's a random speckle field consisting of more than 1,000 modes with a yin-yang symbol superimposed on it, just to show it doesn't matter how the light field looks like. And if the cavity length is tuned for minimum absorption, then it gets almost perfectly reflected. But if the cavity is tuned for maximum absorption, then it gets almost perfectly absorbed. Not only the single speckles or spatial modes, but also the whole field of view. It's almost perfect. There's some gap, but we perfectly understand where it comes from. We rerun our simulation with the actual experimental data, this time considering also some residual effects like the residual reflections on the lenses or the facets of the lenses, which was like 0.13%. And when we considered this in our simulation, we had an almost perfect match between the experimental data and the simulation without any free parameters. So we know what's going on here. So this is a video from the actual experiment. And you see we tune the cavity length, and every time the cavity length hits a multiple of 0.5 lambda, you get this almost perfect absorption of the whole field of view. And then finally the experimenters did some more experiment trying how well this degenerate cavity would work with light fields that are dynamic, changing over time. So they created a speckle field again, but this time with curled up glass fiber, multimode glass fiber, and then they sent the outcoming speckle field through turbulent air created with a heat gun. And again, the CPA still worked. And then they shook the fiber more or less vigorously. And again, it turns out the CPA is really very robust also with these dynamic light fields. Yeah, which is also like to be seen in this image where you have this reflection spectrum for like the static. The right one is with the turbulent air or with more or less vigorous fiber shaking. So this is the video from the experiment where they really shook the fiber very vigorously. And you still see we have this absorption effect. And it's remarkable insofar as the field dynamics here is even faster than the exposure time of the camera, which kind of shows that it also works with spatially incoherent fields. So let me summarize. I tried to show you that CPAs so far are an interesting concept, but the actual use is very limited because they only work with specially designed wavefronts, whereas our new massively degenerate CPA is capable to absorb potentially any wavefront, no matter how complex and even if it changes dynamically. And we think this is an important step towards practical applications, and I'm proud to tell you that seemingly the Physics World magazine also thought so and chose our work to be one of the top 10 breakthroughs in 2022. So before I conclude my presentation, I just want to mention all people involved. That's Kevin Pichler from our institute, who supported the theoretical framework from the very beginning, and our PI, Stefan Rotter. And then from the Hebrew University of Jerusalem, Yevgeny Slobodkin and Jill Weidenberg, who did a tremendous job in building the experimental setup under the supervision of Ori Katz. So with that, I want to thank you for your attention, and I'm happy to answer, or maybe I should say to perfectly absorb all your coherent questions. Thank you very much.
Thank you, Helmut, for this talk. Other questions?
Yeah.
Yeah, thank you. That was really cool to see. I was wondering now, because you explicitly mentioned the application. So with this 4F configuration, are there already ideas how one would make?
I mean, the setup that was actually built with the two lenses is probably not yet ready for being out in the field, because I mean, you can imagine if you have a cavity with plane parallel mirrors and so on, then it's really hard. But if we, I mean, we are also researching different ways how we can build degenerate cavities, which are probably then more capable of being used in practical applications, you know, with glass fibers and waveguides and so on. So this is, we think it's a step toward practical applications. Look, that's interesting. It says the battery is low even if I'm charging it. Well, so, but yeah, more research is required. There are more ideas how to build it really in a small way. Yeah. Thank you. Yeah.
congrats on this great work.
Thank you.
Investing in great work. My question is that how, it's kind of a follow-up question, how crucial is it to perfectly align the mirrors and the lenses as well as have the distance kind of perfectly?
Yeah.
Like how difficult is it to stabilize them to use it?
Yeah. I mean, this was really part of the very long numerical simulations to find out what are the critical parameters, and unsurprisingly, of course, the plane parallel mirrors are the most critical. If you okay, now it died. I even have a slide for that. But if you just if they're out like a 0.001 degree, then it's already you got a problem. It's less a problem with the exact positioning of the lenses, and it's really not at all so much of a problem with the absorber. So I mean, there was this formula of the critical coupling condition, but even if the absorber is plus minus 1%, then it still works very fine. So it's really mostly about these plane parallel mirrors.
Okay, so the vibrations would be very bad.
Yeah.
All of those.
Yeah. I don't.
What about the reflectivity of the second mirror of the cavity? You could imagine like a lost channel.
Yeah, but they checked it. I mean, yeah, it could be a way of cheating, like you say, oh, it absorbs so nicely, but actually the energy goes out in the rear entrance. But no, it was 99.97 something, and actually the experimenters did measure how much light comes out, and when there is maximum absorption, actually there's a little peak at the rear mirror where a little bit more light comes out, but it's negligible compared to the total effect. Yeah, I think you will. Yeah.
So we have like a perfect absorber, no? Which also emits perfectly. It's the whole round, so like the cavity, no? And which also follows like quantum mechanics.
Yeah.
No?
Yeah.
And you can, it's independent on which material you have inside, so you can kind of coat it like this aluminium or with a perfect mirror inside that absorbs anyway.
Yeah.
So how, and it also works for all colors, not for all directions.
Yeah. So why do we need this then? You mean it's a very good question. I mean, here I think it's also interesting if you think about imaging, for example, because you can really make imagine some imaging device where you really get a picture which you wouldn't get in the Hohlraum, right? Yeah. And yeah, but it's just a different concept then, of course. Yeah. I don't know. Julian first, yeah.
I think in principle you could also do this with a multi-mode cavity where you leave the lenses outside of the cavity, right? And you only have the material inside. Is there a technical reason why you prefer that?
Is it degenerate then? Okay.
Multi-mode cavity is degenerate.
Yeah.
So I'm thinking like now you have absorption from the lenses. It's probably an effect that limits your.
Yeah. This was one of the major challenges. Yeah.
I mean, maybe there are other technical.
Yeah.
There are other technical problems. I was wondering if you.
I don't know, but please tell me more afterwards. So maybe we can. Yeah. Yeah.
What about temporal coherence? Could one do the same?
Sorry. What about what?
Temporal coherence. Temporally incoherent beams. Make it work for sunlight?
I mean, one of the limitations that are still there is like it only works at a very narrow frequency band. But we also currently developing a more broadband version of this. Yeah, I mean, there's this concept of a white light cavity where it's basically couple multiple cavities, and then you can broaden this dip. Yeah.
So this is kind of just the thing of is there already ideas with like from the triangle side to do this I don't know the carrot inside a crystal also, so it's like kind of free space or so.
Yeah. I mean, we are currently thinking about like various implementations where we kind of have waveguides coupled to each other and things like that. That would be probably more suitable to really miniaturize them and have a more compact design, which is not then so problematic with the adjustment. Yeah, but I'm sure we haven't exhausted all the possibilities. So any ideas are welcome. Yeah. Okay.